All right, Chem 120 friends, we are going to start with Chapter 4, Section 4. And if you need to go back for some more stoichiometry help, feel free to look back at earlier sections and do some practice problems and look at earlier slides from this lecture. Today we're going to use some stoichiometry principles to analyze a mixture of compounds and find the empirical formula of an unknown compound using chemical stoichiometry. So here we have two clear solutions. We've got sodium sulfate. So we have an unknown amount of the sulfate ion. It's going to be analyzed by adding barium chloride. So here we can see we have two clear aqueous solutions. When we add these two together, it's going to be a double replacement reaction, right? And we know that this double displacement reaction, sodium is going to split from the sulfate, and sodium will join with chlorines to form sodium chloride. And the barium is going to form with the sulfate. I love this glitter pen. So, and notice here it says when the barium chloride is added to the solution containing the sulfate ion, insoluble barium sulfate is precipitated. And we could find that out just by looking at our solubility rules, that barium sulfate is insoluble. And then our clear solution here is the sodium chloride. So how do we measure that? Well, if we have this precipitate that's insoluble, we can collect it in filter paper. So by pouring this solution that's in the beaker, the insoluble product and the soluble product, we can collect the insoluble product in the filter paper, and then the sodium chloride will just be collected in the flask. Then we can dry that filter paper and we can weigh the barium sulfate. So this next question, here we go. We have a sample of the mineral thernodite, and it contains sodium sulfate along with other inert compounds. Okay. So the sodium sulfate in the sample is converted to insoluble barium sulfate by adding barium chloride in excess to the dissolved thernodite sample. The mass recovered is 0.177 grams. So we know how much barium sulfate is recovered. We want to know the mass percent of the sodium sulfate in the mineral. So we're assuming that the barium sulfate that was made, all of the sodium sulfate that we started with was converted to the barium sulfate. So we need to write a balanced equation. Sodium sulfate, and we know that this is sodium sulfate's chemical equation here. I'll switch to a different color that we can see. Sodium we know is always +1, sulfate's a -2. That's why it's Na2SO4. Barium chloride, barium is +2, chlorine's -1, so BaCl2. Same charges apply to the right side, so we've got barium, which is +2, sulfate's -2, +1 and -1. So when we balance everything out, we have a 1 to 1 to 1 to 2 ratio. And again, we're ending with this barium sulfate, and everything that we ended with, we're assuming all of that sodium sulfate converted to barium sulfate. So what are we going to do here? We ended with grams of barium sulfate. So that's our starting point, grams of barium sulfate. Obviously, when we have grams of something, we're going to go to moles of it. Then we're going to compare the mole to mole ratio of barium sulfate to sodium sulfate. Again, if I know moles of sodium sulfate, I can get to grams of sodium sulfate. And then I can find the percent of sodium sulfate in the sample. So let's do that. I'm going to start with my final product here. Grams of barium sulfate, the molar mass of 1 barium, 1 sulfur, and 4 oxygens is 233.4. So again, make sure that our units are diagonal, grams and grams. And that's for every 1 mole of barium sulfate. My mole to mole ratio of barium sulfate to sodium sulfate is a 1 to 1 ratio. So make sure that your 1 for barium sulfate's on the bottom. And then I got to go moles to grams of sodium sulfate. Again, make sure that your 1 mole of sodium sulfate is on the bottom. The molar mass of Na2SO4 is 142. Go through, multiply across, divide going down, and we get 0.108 grams of sodium sulfate. So this is telling me that I'm starting with 0.108 grams of sodium sulfate. Therefore, to find the percent of sodium sulfate, I'm going to take that mass and divide it by the mass of the sample. So of that barium sulfate that was collected, the 0.177 grams, 0.108 grams, which is my amount of sodium sulfate, over 0.177 times it by 100, and we get 61.0% of sodium sulfate in that sample. And again, I started with 3 significant figures, so I'm going to end with 3 significant figures. Moving on, we're going to be able to determine the formula of a hydrocarbon by combustion. So combustion, we know, is hydrocarbon that involves the addition of oxygen, and when it burns completely, carbon dioxide gas and water are always products. So here we have 1.516 grams of a compound containing carbon, hydrogen, and oxygen. So here is the formula setup, but we don't know how many carbons, how many hydrogens, how many oxygens. So it's subjected to combustion. We are given how much products, how much of the 2 products are produced. So we need to figure out the empirical formula for the compound, and given the molecular weight of the compound, we can find the molecular formula. So I'm going to move on here to see where do we start. We were told grams of carbon dioxide and grams of water that we ended up with. So we're going to start with both of these. And I don't know why the hydrocarbon compound wasn't written. So we've got C something, H something, O, X, Y, and Z, plus oxygen to give me CO2 and H2O. So looking at CO2, we're going to go grams to moles using the molar mass. So 1 carbon, 2 oxygens, grams to moles. Now, within CO2, because looking at all of my products here, there is carbon only in this compound. And in CO2, we can say in 1 mole of CO2, there is 1 carbon. So we can say that there's 1 mole of carbon. That's our mole to mole ratio. So grams to moles, moles of CO2 to moles of C tells me my moles of C. We're going to look at the same thing with if I have grams of H2O. Again, if I look at my products, hydrogens are only in that compound. So I can say I'm starting with 1.75 grams of water, grams to moles of water using the molar mass. Notice that in H2O there are 2 H's. So in 1 mole of H2O there are 2 moles of hydrogens. So that gives me my moles of hydrogens. Now the next part is a teeny bit tricky because we can't determine the oxygen in the sample from either CO2 or H2O because, look, there's oxygen in both of those products. So, since there's no way to know how much of that oxygen came from the sample and the oxygen, again, it's in both of the reactants as well, we can't determine the oxygen in the sample directly. So let me show you what we are going to do. We know how much I originally started with. Now, we know that, well, this last slide that we were just looking at, I ended with 0.04731 moles of carbon and 0.1829 moles of hydrogen. So I need to get from moles of carbon to grams of carbon and moles of hydrogen to grams of hydrogen. Because if I know the grams of the C, the grams of the H, then I can find the grams of the O in this original compound, right? If I know grams of C, grams of H, I can find grams of O by subtracting that original mass of that sample. So we converted moles of H to grams of H and moles of C to grams of C. That's where these two numbers came from. So we're going to add those two together and then subtract it from the original 1.516. I'm going to go back to that slide right here. 1.516 grams of a compound that contains carbon, hydrogen, and oxygen. So we know how much carbon and hydrogen. We can find out the oxygen by subtracting. That's what we're doing. So we get 0.757 grams of oxygen. And if I know grams of O, I can get to moles of O, right? 0.757 grams and grams to moles. Again, this is one oxygen, so we're only looking at one oxygen. Now, if I know moles of all of my original pieces, I know moles of C, moles of H, moles of O. Just like when we were finding empirical formula last chapter, we're going to divide all of them by the smallest number, which in this case is the 0.0473. So 0.0473 divided by 0.0473 is 1. That means that my oxygen, that there is one oxygen. And the 0.1892 divided by 0.0473 gives me 4. This is for that's how many hydrogens are in the empirical formula. And lastly, this is for my carbons. We get 1. So I'm going to have C, 1 C, 4 H's, and 1 O for my empirical formula of that original compound. Now, we can go from empirical formula to molecular formula. Easy peasy. We need to find the molar mass of CH4O. And if I know the molecular formula, the formula mass that we're given, you have to be given that. And we were told that in that very first slide. I'm going to go back here. We were told the molecular weight of the compound is this. So we would have to know that to solve this problem. And then we're going to divide that by the empirical formula mass. Well, we know the empirical formula now, so we can add up 1 carbon, 4 H's, and 1 O, which is right here. So the empirical mass is 32.04. So we're going to take that 160.2, the molecular formula mass, divided by the empirical formula mass, round it to the nearest whole number, and we get 5. Make sure and pause the video here so you can double check the math. That means that we're going to take that empirical formula and multiply everything by 5. So that would give us 5 carbons, 20 hydrogens, and 5 oxygens. So there is the molecular formula for that compound that we combusted.